You probably remember from high school mathematics that you can express the scalar product of two vectors x and y as the norm of the first vector times the norm of the second vector times the cosine of the angle that is between the two vectors x and y. Okay, we cannot do that in a difficult space of vectors because we do not have angles there, right? But we have all the rest. We have a scalar product because we have an expression how to compute it. We have norms which can be computed in terms of scalar products. So hence we can now compute angles via the other two things, right? So you can just rearrange this formula for cosine of an angle, or even better, you could say the angle between two vectors x and y is the arcus cosine of, okay, now rearrange this so you get x comma y divided by norm x and norm y. The arc cos function is expecting a value between -1 and 1 because that's what cosinus values look like. And so how do we know that this fraction is always between -1 and +1? How do we know this is an element of -1, 1? Well, we know this from the Cauchy-Schwarz inequality. Right, so the modulus of this thing is between 0 and 1. That's what Cauchy-Schwarz is saying, and that's why if you take away the modulus sign, you get something between -1 and 1. You're realizing that we are now talking about the case of real vector spaces. So our field F is now the set of real numbers. So let's only speak about angles when we have that case. So this is the formula for an angle between two more or less complicated vectors x and y in a more or less complicated vector space with scalar product, or Euclidean space as we say. You're getting a chance to practice this formula and this mechanism in problem 5 it is, on the first exercise sheet. So let's look at that in the next exercise session. Let's recall what we said at the beginning of this last page here. So we said that whenever you have a scalar product, you induce a norm, and with every norm you induce a metric, and together with this metric there comes convergence, Cauchy sequences, closeness, completeness, all that stuff. So we can actually extend our hierarchy of spaces that we saw before a little bit more by spaces that have a scalar product. So the most general class in this hierarchy of spaces is the set of all metric spaces. And let's split those into complete and non-complete metric spaces. Okay. Now a special class of metric spaces are norm spaces. So this is contained in here. We saw that before. The normed spaces. And even more special are spaces that have a scalar product because they automatically have a norm and hence a metric. So spaces with a scalar product. Instead of spaces with a scalar product, we will also say pre-Hilbert spaces. Or we sometimes say Euclidean spaces. Now in the class of all norm spaces, we singled out the ones that are complete and we call them Banach spaces. So the ones I'm showing here on the right are the Banach spaces. And in the same style, you would give the Euclidean or pre-Hilbert spaces that are complete their own name and call them Hilbert spaces. So Hilbert spaces are complete spaces with a scalar product, or you could also say they are Banach spaces with a scalar product.